Luke Barnes and I continue our discussion of our fine-tuning chapter in the Story of the Cosmos book. Last time we discussed some of the many finely tuned parameters necessary for life. Let's now focus on a particular parameter that requires a mind-boggling level of fine-tuning. In particular, you've done a lot of work with galaxy simulations. You've got published works in that area, and you've, I think, shown a lot related to the cosmological constant. Can you speak to that and how that seems to be a clear-cut case of fine-tuning?
Yeah, so there's this number that Einstein introduced in his equations. So he was describing how gravity works, and there was this number that turned up in his derivation called the Cosmological Constant, which back and forth over the next 70 years, sort of went in and 70, 80 years, went in and out of fashion as we weren't sure what the data was telling us, but finally in 1998 we're pretty sure, and since then more data has told us that actually there is this number which represents kind of an anti-gravity force, if you want to think about it that way. It's a way of, if this number is positive, as we think it is in our universe, then the expansion of the universe speeds up. So if you pick a galaxy out there somewhere, we've known since the 1920s that galaxy is moving away from us. And the further away from us it is, the faster it's moving. What this showed in 1998 and subsequently was, not only is that galaxy moving away from us, it's moving away faster today than it was yesterday. So it's speeding up as it goes. Okay, so now we think about fine-tuning, we think about what would we expect, we think about other ways the universe could have been. Let's take this number and let's change it and see what happens. And there's sort of a handle we can get from fundamental physics if this number comes from what's known as vacuum energy. And the idea is, we know that there's things like particles in the universe, and we know that we can take those out of a given region, we can create a vacuum, but it still could be the case, and there are indications from some theories that is the case, that there's still energy in there.
Isn't that really widely accepted, that there's residual energy?
Well, now you've got to an interesting point. So the problem with that calculation is, you take this idea of quantum fields and you say, all right, well, what's happening in empty space when there's no particle there? And if you apply it in this sort of the empty space around an atom, near an atom, that calculation works beautifully. You get something called the Lamb shift. And so we're like, hey, hooray, quantum field theory works. Let's apply it to properly empty space. And then you get, if there's any energy there, it would act like a cosmological constant. So maybe that'll explain this expansion. The problem is that the amount, the value of this number that you would expect, just from this naive sort of calculation, is larger than the value in our universe by a number with 120 digits in it. So 10 to the power of 120. I guess it's got 121 digits in it, but whatever. We'll give a digit or two here or there. And so what we were doing in the simulations was saying, all right, well, what happens if you change this number? Now, we've known some sort of pen and paper arguments. The short story there is that in our universe, gravity brings things together. So you start off with a universe that's almost smooth, and then gravity makes it into galaxies. Once the expansion of the universe starts to accelerate, that process shuts off. And so the larger this cosmological constant is, the earlier in the universe that process shuts off. And in particular, you can easily push it early enough that it shuts off before it started. And so no galaxies, no stars, no planets, no complexity, because there's nothing stuck to anything else. And so it's that sort of level. We wanted to look specifically to use the best sort of simulations we have about how structure forms, supercomputer simulations, to really look in detail about what happens, not just if you change it by some enormous amount, but let's change it by a factor of 10, a factor of 100, a factor of 300, in that sort of range, just to see what's going on. And it's a way of sort of testing some ideas about why the number might be the way it is.
And we have other videos with more details on this on our YouTube channel, but just briefly, so your findings actually were maybe that the cosmological constant was a little bit less finely tuned than was previously anticipated, although it's still ridiculously fine-tuned. Right. Can you comment and briefly summarize that briefly? Yes.
So we were expecting that if you change the cosmological constant, say by a factor of say 30, then that's pretty much the end of that. So that's kind of what we expected was going to happen in our universe. It's about 1 billion years ago when the cosmological constant takes over. So there's been 12 billion years of time for structure to form, but make the cosmological constant 30 times larger. That amount of time goes back in time by a factor of about 5-ish, and so instead of and so you have much less time to make an interesting structure. What we found in the simulations was actually we were still getting a reasonable amount of sort of stars and those sorts of things, up to a cosmological constant 300 times larger, which we didn't quite expect. It was kind of hard to do these simulations after a certain point. They sort of grind to a halt. So I'd love to do 1,000 times larger, but that one's for another day. So that was kind of interesting. The reason why that, it doesn't make much of a difference to fine tuning is that's comparing another value of the cosmological constant to our universe.
The 120 digits.
Yeah.
That comes into play. You throw out a few digits, no big deal. It's still fine.
Yeah, if you're thinking about the total possible range, it's that 120 digits.
Right.
And so 30 times larger, 300 times larger, go 10,000, 10 million times larger, who cares? So in particular, there is a paper, it's a sort of analytic argument rather than our simulations, but from Fred Adams, who's an astronomer, I think at Michigan, looking at, okay, let's not just change the cosmological constant, let's try and change everything else we can to possibly do it to try and get. And he somehow scraped together, I think, maybe 10 or 20 orders of magnitude, maybe a few more, but 120 orders of magnitude. It's
no way to compensate once you get past a certain point.
Yes.
And so this was somewhat interesting because there's a famous prediction a number of years ago by Steven Weinberg, actually pretty clever, where he was seeing this fine tuning of the cosmological constant, seeing that it looks difficult to explain unless you posit a multiverse, these other universes with varying constants.
Yeah.
And some folks like Leonard Susskind even sort of credited this as maybe a soft fulfillment of a multiverse prediction.
Yeah.
Because he got it right within an order of magnitude or so. But your work is showing, well, maybe there was a wider range. Maybe it's almost should count against the multiverse if you're viewing it as a random selection among like-many universes. It looks more finely tuned than is necessary.
Yeah, maybe. I mean, it's a hard calculation to do in general. In particular, it depends a lot on the details of the multiverse model.
Yeah.
But so the idea here is, okay, if you think that the reason why our universe has just the right value is that there's lots of other values out there, and we just sort of won the cosmic lottery. What you should be able to do if you've got a specific idea about how that plays out, about exactly where or what the population of other bits of the universe is, you should be able to say, all right, let's in theory just get out our clipboard and go around to all these other universes and say, if anyone's there, ask them what cosmological constant they observe, and then you've got a survey which basically makes up a prediction of what you would expect. So what we were getting back when we sort of chugged through all of this for some fairly generic versions of the multiverse theory was to say it's probably, you'd expect it to be 50 times larger than what we saw. And the reason for that is, okay, as you increase this number, you get less structure in the universe. But there's also, if you're just picking this number at random, there's probably more universes out there with 50 or 49 or 47, 21. Yeah, there's probably more universes out there with those larger numbers because they're larger values. There's more sort of, if you take uniform, there's more values between 10 and 100 than there are between 0 and 10. So if you just sort of pick them at random, you'd expect more of those larger values. So you're more likely to be a rare life form in a more common type of universe than you are, as we are, being a more common type of life form in a more rare universe with a smaller constant. So trying to put that together, I mean, it's still in the ballpark. I mean, relative to 120 orders of magnitude, to miss it by a factor of 50 is still pretty amazing. So,
sure.
So maybe someone can come up with some explanation as to why it is the way it is, and that's entirely fine in terms of fine-tuning argument. I mean, but we'll just take the best physics we have and see what happens. And if better physics comes along tomorrow, we'll have a look.
It's probably fair to say it's not impossible that a multiverse could naturally explain the cosmological constant. This would just be one more way in which it would need to explain this in a naturally non-finely tuned manner. It's like sort of another obstacle.
So, in particular, this idea of a multiverse. So the way I like to think of this is, what does that do to fine-tuning? Well, it might explain the fine-tuning of, say, the cosmological constant. But the way it's going to do that is by taking the cosmological constant, which we think of as just some fundamental number, and turning it into some sort of variable, something that could change from here to there. And so we've got a totally different theory on our hands now. And so, all right, if that's the theory, then we'll look at that and see if that's fine-tuned. You just go to the best level. But it's not necessarily the case that it therefore means the universe is less fine-tuned than we currently think it is. So a way I like to think about this is think about the Earth and the Sun. I think if the Earth was, say, I think it's about 5% closer to the Sun, then it would probably be too hot for liquid water. Okay, so that sounds like fine-tuning, right? Well, you might say, okay, but there's lots of planetary systems out there.
Yes.
And so there's probably at least one planet for every star. an entire universe full of a lot of stars. So there's probably at least a few planets that get this right. That's not just surprising.
I would say, yeah.
The reason why that doesn't mean that the universe isn't fine-tuned is because, okay, you've taken some number, the distance from the Earth to the Sun, or a planet to the Sun, and said, okay, there's lots of other universes, lots of other planetary systems out there. What that should lead you towards is the next question. Okay, there's lots of different ways to put a solar system together. Well, now let's think about how you put a universe together. And it's that sort of question that leads you then to the fine-tuning of the fundamental parameters on a universe level as far as we can see. If you want to then just go, okay, let's just go a step deeper, right? There's not just lots of solar systems, stars. There's lots of universes out there. All right, fine. Show me a theory, and then we'll go even deeper. We'll keep drilling down on this question. And maybe we'll get a different answer the next time around, but there's no guarantees.
All we can really do is evaluate the physics that we know, the universe that we know.
Yeah, absolutely.
But theoretical physics does define a range of possibilities, and that's what we're comparing against. And just to be clear, we're not making the kind of environmental arguments that, planets with water are rare. We're not getting into any of that in this chapter of the book. It's all about the fine-tuning of the initial conditions and the constants being within narrow ranges. We do also touch on laws. There's a number of ways. Can you give us maybe just real quickly, and then we'll close out soon here, but a couple of examples of how the laws could have been different and messed things up for life?
Yeah, so, what we'd love to do is just take everything we know about physics and just change it all and let's see what's going on. It's quite hard to do that systematically, but we can think of a few ways to change things. We know that the fundamental laws of our universe are described by quantum mechanics in some way or another, and one of the basic things about quantum mechanics is we know one of the reasons why it was proposed in the first place is because the physicists couldn't explain the structure of matter, and particularly the stability of matter, using just ordinary classical pre-quantum the theory of electromagnetism. So in particular, we have this picture of here's the positively charged nucleus, here's the electron going around the outside. If you describe that system in ordinary classical electromagnetism, it's not stable like a sort of solar system going around. The electron will give out light, it's constantly radiating, and it will just spiral into the nucleus, and your atoms aren't stable anymore. And so we need...
And this happens in very much a fraction of a second.
Yeah. I think it's something like 10 to the minus 13 seconds, or something.
That sounds about right.
Insanely small number. There's various other things. If gravity was repulsive, then the universe would disperse structure instead of forming it.
If the strong force worked at large distances, and
so there's that force that holds nuclei together, but because it's only got a limited range, you only get a limited size of nuclei. And so you get the periodic table. You can have one proton all the way down to 92 for naturally occurring elements, and in the lab we've pushed that out to 100 and something. But you can't just keep on going. But if the strong, it's easy to imagine a strong force, which is just if the strongest thing in the universe was just able to bind everything together as much as it liked, you would just get huge agglomerations of matter with no structure. It would just be massive balls of matter. That would be all there is to it. And so you can ruin things with the laws. It's harder to be systematic in this case, but there's no example of laws that we can write down where you get life no matter what, where you don't need to fine-tune anything. Anytime we look at another set of laws, if it can make life at all, if it can make any sort of complex structure at all, we have to do some hard work turning those knobs and dials.
All right, so then just coming back to Dawkins' quote again, and we'll close it out here, but so when we examine the universe at bottom, we try to do what Dawkins suggested, we do find that it doesn't seem to just be blind and indifferent without purpose. At least there's some pattern of coincidences that just happens to be right for life. And so as a theist, I do see that as at least some evidence for God. It looks like it was rigged in some sense. It seems improbable.
It at least sort of lights a fire under the... If you had Dawkins' idea, but you were just looking at DNA, we'll have a look deeper at physics and what you would, what sort of universe would you expect there to exist if naturalism were true, if there was no design, no purpose. Well, not one with DNA in it, one that was dead, no structure or anything at all. So the fact that ours isn't that kind of universe should send you out looking at least to see whether there's some other options to explain the data.
Exactly. Well, thanks a lot, Luke. Appreciate your time.